So today we will continue from last class. Uh, we will try to solve a problem in shafts. If you recall from last class, we went through different criteria.
Sorry, I can't do that.
1 second. Okay, so we went through different criteria like ASME elliptic, Soderberg, Gerber, and Goodman equations for shaft design. Okay, so there are two formulas in each case, one for calculating factor of safety and another formula for directly figuring out what is the diameter of the shaft. Besides these four cases, except Soderberg, all the other three, ASME elliptic, Gerber and Goodman equation, we also need to check for yielding phenomena. To check for yielding phenomena, we use this formula to calculate what is the yield factor of safety, just to ensure that we are also within the yield limit. Okay, so now we are going to apply that. You have a machined shaft shoulder. So why is the condition machined is being given here? To take care of the Merin factors, okay, especially Ka, small Ka value. To evaluate that, you are given shoulder shaft with a small diameter D. You have 1.1 inches and the large diameter D 1.65 inches. Here you are given in English units, and the fillet radius is given. So this data is given so that we can calculate the fatigue stress concentration factors. Okay, so if you take the formula, you can see Kf, capital Kf, capital Kfs. So these are fatigue stress concentration factors which need to be obtained from Peterson's graph and the notch sensitivity factors. Okay. The bending moment is 1260 pound force inch. So whenever a bending moment is given for a shaft, you should automatically understand it is a completely reverse bending moment load and a steady torsion moment, which is constant value, the mean torque value, Tm. Okay. The heat treated steel shaft has an ultimate SUT value and SY value. You are given the reliability goal is 0.99. Again, this is for KE, small KE value. Okay, so determine the fatigue factor of safety of the design using each of the fatigue failure criteria described in the section. Also, determine the yield factor of safety. Okay. So to determine each factor of safety, so let's go to one of the theories behind here. So we can see ASME elliptic, we have this formula. We know that this term will go to 0 because amplitude of torque is 0, and the mean torque term will also go off because it is completely reversed loading. So we have these two terms here, and we have to determine SE. SY we are given, but we have to estimate SE value. We have the diameter. We will consider the smaller diameter here and then evaluate what is the factor of safety. Okay. Here. Let's go back to the problem here. Let's try to solve it. Okay. We are given machined shoulder shaft. First of all, we note down the properties which are given. SUT is equal to 105 kpsi. And SY is equal to 82 kpsi. Then we need to evaluate SE. We know what is the formula for SE, but in order to determine SE, we need SE prime. SE prime will be 0.5 times SUT according to the empirical formula. This value is less than 200 kpsi or 700 megapascal. Therefore, we can use this formula. So that gives us half of the value. Five kpsi. Now we need to determine each of the 6 factors. So we go by using the formulas. Let's see here. If we have the formula over here, Ka, okay, so this is the new version of the book. I'm going to work with the old version of the book so that we may have the same Meron factors. Okay, so let's first figure out where the Meron factors are given, formulas for Meron factors. I'm just going to use my okay. Okay, so we have it here. Let's go to the table. It is machined and we are using English units. So 2.7 here is the formula. 1 second. A SUT raised to the power B, and the A value is from the table here 2.7. SUT value is 105 raised to the power B. B is minus 0.265. So let's calculate this in MATLAB. Let's clear everything and then start from beginning here. So you first calculate Ka, the Meron factor. A is 2.7 times 105 raised to the power minus 0.265. 0.7866. Let's calculate KB. KB will be according to the formula given here. Okay. We will have to consider the smaller diameter. So let's go back to the here problem here. Given we are given small d is 1.1 inches. So let's see here. Now we use the formula. Bracket open. Since we are in inches, 1.1 inches, we are within this range. We have to use this d over 0.3. 0.3 raised to the power minus 0.107. Small kb 1.1 over 0.3. Raised to the power minus 0.107. Yes, we have 0.8702. Let's say Kc see the formula for Kc. We have this. Let's read the problem and see what kind of load we are applying. We are applying bending moment and torsion. So it is a combined load. In the case of the combined load, we cannot use any of these individual values. Rather, we take Kc equal to 1. So directly 1, since it is a combined load. Let's go for Kd. Kd is temperature. Since no information is given about temperature, we take Kd equal to 1 by default. Okay, Ke is the reliability factor. We are given reliability 99%. And from the table, we directly take it. We can see here 0.99, which is 99%. 99% is here, and corresponding to 99%, Ke is 0.814. Small kf, which is a Meron factor, again this is not equal to your capital Kf. Yes, the small kf value is taken to be 1. Now we can calculate Se by multiplying the factors Ka, Kb, etc. Multiplied by 0.8702, Kc is 1, Kd is 1, Ke is 0.814 and Kf is 1, and then multiply by Se prime, which is 52.5. So multiply all this and we will get what is our Se value in our case. So it should be Ka, Kb, Ke is 0.814 and there is no other value, so we need not worry. And I'm also going to put 0.5 times, and we are given the originally SAT value, which is again 105. 29.2520. So we have the SE value. We can go ahead and try some of the formulas, what we have already, ready-made formulas. If you look at here, let's try the ASME elliptic formula. So according to the ASME elliptic formula, you can try your n, 1 over n should be equal to 16 over pi d cube. Okay, but before that we also need to take care of Kf, capital Kf. We haven't calculated capital Kf. So to get your capital Kf, we need Kt and Kts. Okay, so this we obtain from the Peterson's graphs. I'm not going to go through that. So let's see here. For the given ratio here, fillet radius, they have calculated all the values. You can see Kt equal to 1.68, Kts is 1.42. They have obtained these values from the graphs, Peterson's graphs. Also, the notch sensitivity factors Q and Qs, they are also to be obtained from graphs similar to your Peterson's graph. You get your Q value 0.85, and Qs value is 0.88, 0.88. Okay. Now your fatigue stress concentration factor is going to be 1 plus Q times Kt minus 1, and using that formula you can evaluate these values. Just substitute and you will get it. Kf is 1 plus Qs times Kts minus 1. And again, calculated value is given as 1.37. Now we are ready to apply the formulas after calculating all these quantities. Let's go to ASME elliptic here, 16 over pi d cube. We have the d value 1.1, smaller value, 4 times Kf value was 1.58 times MA over SC. Okay, what is MA in our given problem? It depends upon the applied load. So let's go back and check here. We are given here bending moment is 1260. Okay, so since this is the completely reversed loading, that means this is the max value, M max is equal to 1260, and we can directly see here, since it is a completely reversed loading, this value also should be equal to the amplitude, while M mean value is 0. Take the torque, you have the T mean value, since it is a steady, 1100 pound-force inch, and the amplitude is 0. So directly apply this. We have 1260. Okay. Go back to the formula. For MA, I apply 1260 divided by SE value 29.252, the whole square, plus we have 3 times KFS. KFS is 1.37. Multiply that by the mean torque value. Again, what is the mean torque value? We go back to the problem. We have 1100. Divided by SY value, the yield strength value, 82. The square. And then everything under the root, square root term. Okay, so let's calculate this. Again, this should be 1.1 here. So your N should be equal to inverse of this entire quantity. So that will be pi over, sorry, pi times 1.1 cube over 16, and in the denominator we have the square root term here. A big term here, 4 times, we have 1.58, let's open up a bracket, and square times 1260 divided 1260, yes, divided by SE. Then we have 3 times, bracket open, and square of this Inside the bracket, we have 1.37 times 1100 divided by 82. That should give you the, okay, so what we are doing wrong here. Be 1 over n. The entire thing should be in the denominator, right? 5 times. Okay. Okay, so I think we have some units issue. So let's do one thing. Let's read the problem. We have all the values, material properties in kpsi, while the moment is in pound force. So we have to divide these quantities by 1000. Okay, so that's what we did a mistake. The properties are in kilopounds, while the forces are in just pounds. So there is a factor of 1000 over here. So we need to include those factors in the denominator. Okay, so then it would come out right, or multiply the properties by 1000. So either way, this is correct. So let's change the formula here. In the denominator should have 1000 over here, and this should be 82,000. So that gives us 1.8696. So be careful about the units. If you are not careful about the units, you will get the wrong answer. So let's check the fatigue factor of safety according to ASME elliptic. These calculations here, I think these are for Goodman criteria, and we can see here for ASME elliptic 1.88, and we get 88696. So quite close to the value given here. Okay, so the formula, you can see they are different depending upon which particular criteria we have taken. We have taken according to ASME elliptic, this is the fatigue factor of safety. So let's also check for yield factor of safety. You can use the same procedure to calculate other quantities. We also need to check for the yield factor of safety. For yield factor of safety, the formula which we have is right here, and we can see that the mean stress will again go to 0, and the amplitude of shear stress from torque will also go to 0. Again, last class we learned that the shafts are usually have the load applied. Whatever load we apply, usually the bending moment load is completely reversed, and therefore the mean stress will be 0. And in the case of the torque, we usually have a steady state of torque, which means we will have mean shear stress and amplitude of shear stress will be 0. Okay, so what is sigma max prime? Why do we need to find that? We need to find that to calculate the yield factor of safety. Either we can figure out these values, sigma A and tau m separately, or directly use the formula given here. So if you are using this formula, again this term goes off, and then we have the torque amplitude, which is 0. So let's substitute this formula and evaluate sigma max prime. So before we calculate this, to calculate the yield factor of safety, we have to calculate sigma max prime. So we have square root of 32 times KF value. The KF value we already know, 1.58. And we have MA 1260. Pi d cube. Notice that I am always substituting the smaller diameter, because when you use the fatigue factor of fatigue stress concentration factor, we should consider only the smaller diameter of the shaft for all calculations. The larger diameter will have lesser stress, while the smaller diameter part of the shaft will have the higher stress always. So we have to use the smaller diameter. Okay, square here, square this term, plus we have 16 times KFS. Don't forget the factor 3 here before that. 16 times KFS 37. And then we have the mean torque 1100. Divided by, again, pi d cube entire square, and then close the bracket, and we have 1 over 2 square root of that. So let's calculate this quantity. Square root, then 32 times 1.58 times 1260 divided by we have pi times 1.1 cube square inside the square root. We can take it outside commonly out, and if I take it outside the square root, I will just have here pi times 1.1 cube. Okay. Here we have 3 times 16. .37 times 1100. So this is your S max. By the way, we have the sigma max result here according to the formula what we have seen here in pounds per square inch. We want in kpsi. So in order to do that, I have to divide by 1000 here. So let's see here in the denominator, I multiply by 1000. So we can take a common factor 1000 outside and put it here, and then calculate it, and that will give you in kpsi directly 18.2172. kpsi. Okay, so we have the sigma max prime We can evaluate what is the yield factor of safety. We know what is SY. Let's see here. Back to the slides. We have SY over sigma prime max. Von Mises maximum stress. That is what we have calculated here. What is the SY value? 82. Over 18.2172, and you will get what is the yield factor of safety. It is definitely greater than 1. Therefore, the shaft will not fail. Okay, so let's see. Go to the MATLAB, and yield factor of safety is going to be 82 over sigma max prime, 4.5012. So again, no failure, and this is the answer we get. Let's see in the problem, the yield factor of safety yield factor of safety 4.5. Okay, exactly, that's the result we get. There is an alternative formula to calculate sigma max prime approximately. Just add the amplitude and the mean stress. You will get an approximation of sigma max prime. Okay, so it won't be exact like what you have calculated using this formula. So you can see here we get with the exact formula 4.5, with the approximate formula we get 3.25. Okay. Okay, so this is a very simple example of calculating fatigue factor of safety when we know what is the diameter of the shaft. In design situations, we want to figure out what is the diameter of the shaft. So which means what? We do not know what is small d, capital D. Usually the shafts are stepped shaft like this. We will have a fillet radius R. Usually we will have a small d and a capital D. So this is a simple shaft where we have a single shoulder. In reality, we will have shaft with many steps, and we will have many diameters to figure it out. But let's take the simple case. We do not know small d, we do not know capital D, we do not know R. So if we do not know any of these dimensions, what are the problems we could face when we come up with the equations? In the equations, if you recall, we used Kf, Kfs, which was obtained from Kt, Kts, and Q and Qs. Now, if you don't have any of these dimensions, none of these stress concentration factors can be determined. In addition, we also have the Merin factors. Okay, in the Merin factor, specifically the small kb value, which is the size factor, cannot be determined. So how do we proceed? So let's see here. Stress analysis for shafts is highly dependent upon stress concentrations, which means our design must take into account any fillet radius change in geometry, and it must also take into account the stress concentration factors. Otherwise, our design equations will be wrong. But to start with, we have none. Stress concentration factors depend upon size specifications, which are not known the first time through a design process. Okay, so what do we do? Standard shaft elements such as shoulders, so this is a shoulder. In addition, a shaft might also have keyways. We have seen In order to connect a hub to the shaft, we need key seats, okay, or keyways. So that is what it is talking about. This also lead to stress concentration effects. Keys and standard proportions make it possible to estimate stress concentration factors before determine the actual sizes. So there are standard shaft elements. Your key seat size is standard. Based upon the standard size, there can be estimated values of KF, KFS, KT, etc. We can use those estimated values. These estimated values will be given in your table. Okay, so just as a data, you will be given as a table of data, and then you can use that initially to evaluate your design. Okay, all right. So this is the data we will be using for shoulder fillet, which is sharp. Okay, that is, what is sharp? So if your radius here, fillet radius, is very small, then it is considered sharp. How very small? If the ratio R over D, if this ratio is equal to 0.02 or lesser, then you will use these stress concentration factors. For the static case, okay, KT and KTS values, you will use these values. If it is well rounded, maybe equal to 0.1 or greater, then you will use these standard values to start with. If you have a key seat is the place where you put your keys in the shaft. So these are usually created by milling operations on the shaft surface, and again they lead to stress concentration effects. Again, due to that, KTS, you can see that. Again, different kind of key seat, and then you also have a retaining groove. What is a retaining groove? In a shaft, in order to locate and retain the bearings, you will have retaining grooves. Retainer is installed inside the retaining grooves. Okay, so let's see retaining ring grooves. Let's see an example. So this is a example of a retaining ring which positions your bearings or other components on the shaft, and these rings will be installed inside a groove of the shaft. Let's see a better picture here. So this is the groove. So this retaining rings are installed inside this groove, and they are used to position certain elements on the shaft, for example your bearings. Okay, so if you have a retaining ring, you can see very high stress concentration effects. So these are the things you will use for standard design. Whenever you have a shoulder again or a change in geometry, it leads to stress concentration effects right at the corner here, and there are ways to reduce it. We can provide a what you call as an undercut in the larger portion of the shaft, or you can provide a relief groove on the larger portion or the smaller portion. So these grooves also reduce the stress concentration effects, and there will be a smooth variation in the stress between the larger portion and the smaller portion of the shaft. So let's see a real design process. This is an example problem. You are to design the shaft which is provided here. So designing of shaft usually involves calculation of the diameters D1, D2, D3, etc. All these diameters have to be calculated. And before you start calculating the diameters of the shaft, the length of the shaft will be fixed by the arrangement of the shaft accessories. For example, if you are installing gears onto the shaft, bearings onto the shaft, these lengths will all be fixed by some other criteria. So usually you will have all these lengths ready in hand, and you know that you will have to provide a shoulder on the shaft at particular lengths. So you are given this data for all these points. You have all the length of the shaft provided here. You can read starting from 0, 0 0.25, 0.75, etc. Okay. And it is also given here. You will install bearing A and B over here. There are two key seats. You can see this will lead to stress concentration effects. The gears are there, and let's see how to figure out what should be the diameters. Now through gears 3 and 4, torque is transmitted, and they will also lead to bending moment loads. So what kind of forces act between the gears? For example, gear 3 may be attached to gear 2, gear 4 may be attached to some other gear, and there will be transmission of loads between them. This example problem is a part of a larger case study. Okay, so you can read chapter 18 if you want. A double reduction gearbox design has developed to the point that the general layout and axial dimensions of the countershaft carrying two spur gears has been proposed. So it has been proposed already. The length of the shaft is already decided. The gears and bearings are located and supported by shoulders and held in place by retaining rings. So you have retaining rings here. So you can see the groove, and there is a retaining ring installed here. Again, there is a groove here, retaining ring, groove here, retaining ring. The gears transmit torque through keys. So the gears are mounted, and the gear is coupled with the shaft with the keys, and therefore you have key seats here where the gear is installed. The gears transmit torque through keys. The gears have been specified as shown, allowing the tangential and radial transmitted load through gears to the shaft to be determined as follows. Okay. So what you have here is the tangential load. There is a gear 2 over here, and there is a gear 5 over here. Between 2 and 3, there is a transmission of load, and because of this load, you have the tangential load and the radial load on the gear 3. Similarly, you have the tangential and radial load on the gear 4. Okay, again, let me get a picture of spur gears. What are spur gears? Spur gears usually have the teeth which is parallel to the axis of the gear. You can see in all spur gears you have teeth which is parallel to the axis. Let's try, for example, helical gears. In the case of the helical gears, on the other hand, you can see the gear is not parallel to the axis of the gears. Okay, so that is the difference. When you have helical gears, you will have three-dimensional loads. You will have x, y, z. So if you consider along the axis, there will be one load. There will be also loads which are perpendicular to the axis, maybe in this direction and the vertical direction. So you will have three different loads. But if you take the spur gears do not lead to any axial load. They will lead only to the radial load. You can see these two gears, when they mesh against each other, there will be a tangential load here, and there will also be a radial load because of the slope on the gear teeth. Okay, so there will also be radial loads. So only these two loads are there, and therefore in the problem we consider only these two loads here, tangential and radial loads. Okay, so the subscript T stands for tangential, R for radial respectively, and the subscripts 2, 3 and 5, 4 represent the forces exerted by gears 2 and 5 on the gears 3 and 4. So gear 2 is here, it exerts some load on 3, gear 5 is here, it exerts some load on 4. Proceed with the next phase of the design, in which the suitable material is selected and appropriate dimensions for the section of the shaft are estimated, based on providing sufficient fatigue and stress capacity for the infinite life of the shaft. So the shaft must have infinite life. That means my fatigue factor of safety should be greater than 1. And we are going to assume the minimum factor, safety factors to be 1.5. This means even the yield factor of safety minimum should be 1.5, or the fatigue factor of safety must be minimum 1.5. So depending upon whichever criteria you take, you will have to consider 1.5. So how do we start the design? As usual, we need, this is a 3D problem. Remember, this is a 3D problem. So we will have to draw the free body diagram for the shaft, identify all the forces. You have reaction forces, just like you assume this is a simply supported beam like structure, and you will have the different forces here. So first fix your coordinate system x, y and z, and you can see in the y direction and the z direction you have reaction force at A, and similarly reaction force at B at the y and the z direction. There are 4 unknowns, and again there are 4 different forces you can see here: the radial, the tangential along the z direction, the radial along the y direction. Okay, so we have all these loads. We can figure out the equations. What are the equations to be considered? We can see by considering only the radial loads in the y direction. We can figure out RAY and RBY easily by writing the equilibrium equation. RAY plus BY should be equal to W radial here plus W radial there. We can take moment about A and then figure out what is RBY. And similarly, we can figure out for the Z direction forces. So once you figure it out by writing the equilibrium equations, these will be the forces. Next step is to draw. First of all, we need to figure out what is the critical location. To do that, first we have to draw the torque diagram. We need to draw the bending moment diagram to figure out the stresses due to bending moment. In any shaft, you have 2 different forces. One is the, or 2 different moments. One is the torque, the other one is the bending moment. So for the torque, for the case of the torque, we can easily figure out that the torque is applied between the 2 gears. So it should be the tangential force times the radius of the gear. So we are already given what is the diameter of the gear. The gear diameter is given to be 12 inches here. 12 inches divided by 2 into the force, tangential force here, 540 times this value, 12 over 2, will give me what is the torque. So 540 times 12 over 2. What is that? 3240 pound force inches. We can also check with the other case. In the gear 4 case, let's see the tangential load 2431 times 2.67 over 2. So 2.67 over 2. We can calculate times. And what is the tangential load? We have 2431. We get let's see here, 3245. And what is the value we calculated here? 3240. So there is some minor difference between the torque. There is some torque imbalance. That's okay, because usually you will have to overcome friction, and that will whatever difference we have, the torques will cancel. So either we can consider 3245 or 3240 for our design purpose here. We are considering 3240 and we are assuming the torque will be 3240. Okay. So from the point where you apply the tangential load, which is at the center of the gear, to the center of the other gear, we have a constant torque, steady torque here. There is no variation, and the torque outside is 0. So this is the first step, torque diagram. If you go for the bending moment diagram, bending moment is in two different directions for the circular shaft. So we have to find bending moment about Z, bending moment about Y, and then find the resultant bending moment. Okay, also the shear forces will be in two different directions. The shear forces, we are not going to worry about it. Rather, we need to worry about the bending moment in two different directions. So about with respect to y-axis, this is the bending moment diagram. We can calculate this. And about the z-axis, the bending moment is given, and we have to get the resultant bending moment by squaring and adding them to find the resultant bending moment. What is the resultant bending moment? It's going to be my square plus mz square. So using this formula, we can at each location find what is the resultant bending moment and get the values here. So 713 square plus 230 square under root will give me this. In the same way, adding those other quantities will give me what is the resultant bending moment. Why do we need the resultant bending moment? Since it is a circular shaft, we can get the resultant moment and then use that resultant moment to calculate our stresses. Okay, so here we can see at each of the point what is the resultant moment, and we can use these values to estimate what should be the diameter of the shaft. So let's identify one point first in the span of the shaft. Okay, there is a shoulder right in the point I. If I choose this point I right here, I can try to determine the diameter d5 by considering the stress concentration effect over here. Okay, so initially we do not have any values. So what do? I use this table. We have a shoulder fillet. We are going to assume a well-rounded or sharp fillet, whichever you want. Worst case scenario, a sharp fillet, we can assume that, and take KT value and KTS value as 2.7, 2.2 respectively. Okay, and we do not have any axial load here, so we will take only these two values and consider that for calculating KF and KFS. So let's go back here. KT and KTS values are extracted as 1.7 and 1.5. So they have not taken the worst case scenario. They are assuming well-rounded shoulder fillets. Okay, so 1.7 and 1.5. How about Q and QS? Since we cannot estimate Q and QS without the radius, what we are going to do is we are going to take the worst case scenario where Q and QS are 1 and KF and KFS values assume the maximum values of KT and KTS. So this is the worst case scenario. Again, we have these values. Now we can apply one of the failure theories, any theory you want, Soderberg or any other theory. But before we go there, we have to estimate SE for the given material. For the design, you choose some inexpensive material, 1020 cold drawn steel, or you may choose 1040 steel, whichever you want to, and you provide the material properties, then you calculate all the 6 Merrin factors and estimate what is SE. So here they have decided at point I to use the Goodman criteria and calculate what is the diameter. Again, if you go back to the list of formulas which you were provided, in the case of a Goodman criteria, you have a direct formula to evaluate your diameter. Again, your amplitude of stress is there, this term will go off, and the mean stress will also Well, only these two terms you have to consider and calculate your D. So let's go back to the problem. Okay. Let's see here. Yes. So we were right at point I. If you recall, we are calculating at point I. We want to estimate the diameter at a point I according to the calculations. Okay, apply the formula, and when we calculate, we get D is equal to 1.65 inches. Okay. Now, this is the calculated value, but in order to design for a shaft, usually you must use some standard sizes. So where do we get these standard sizes? Let's see here. Go back to some appendix. We need the standard sizes. Maybe in appendix B. No, should be in appendix A. Preferred sizes and Renard series. So this is what we want to see. A17. Go to table A17, and usually this gives you all the preferred sizes. So you have 1.625 or 1.65, I guess, according to our calculations. We have 1.65 inches. Let's see, we have the standard size 1.65. This is in inches. We have, no, we don't have here the standard size over here. Let's see. Again, we don't have here. Okay. All right. So we are not given according to the series over here the standard sizes. Let's see again anywhere else. Okay. So from some table which has the standard sizes of the shaft, he has obtained over here, instead of using 1.65 inches, the standard size given is 1.625, and he has chosen 1.625 inches as the standard size, even though the diameter is lesser. Now, since he chose the lesser diameter, now what he is going to do is he is going to check for the factor of safety for using the D value equal to 1.625. Okay. Now, before we go there, which is the diameter? He has calculated D5. So this is the diameter he has calculated. So let's see. No, I think we came forward a little bit. Okay, 1.65. He has assumed 1.625. Now he is calculating the ratios D over D, R over D, etc. All the other ratios. He evaluates what is the fillet radius. Okay. Now let's see. Here we are going to write it here. D5 is equal to 1.625. This is page 35. Let's go back. We want to also estimate D4. Okay. So our D4 will be your capital D here. Capital D. and we want to estimate what is D4. So using the ratio given in the table, capital D or small d as 1.2 standard size, he is evaluating the capital D or D4 to be 1.95 inches, and the standard size gives us 2.0 inches. Okay. Also, we can estimate based upon R over small d ratio, what is the R value? Comes around 0.16 inches. So now we have estimated all these values. Now we can also estimate KT and KTS values from Peterson's graph. Similarly, we can estimate KF and KFS after we figure out what is Q and QS. Again, he is estimating based upon these calculations what is the SE value. He gets 25.1, and then he is calculating what is the fatigue factor of safety using Goodman criteria, 1.56. So this is fine. Since it is greater than 1, the factor of safety is greater than 1.5. Remember, the required factor of safety should be greater than or equal to 1.5. Since it is greater, then our calculations are okay. He is also checking for yield factor of safety. This is also fine, which is greater than 1.5. So the calculations are fine for the given design. Now also check this diameter at the end of the keyway. Okay. Now if you look at the design, we have a keyway here. The presence of the keyway leads to very high stress concentration effects. We have seen that here. Where is this? Key seat 2.143. So we need to check for that as well. So let's go back over here and let's check again with the key seat. And now for the key seat, we assume from the standard table, what are the sizes? R over D is 0.02. Okay, for the key seat, this is the one they have assumed. Let's go back to the table. 0.02. So using this ratio, okay, here using the ratio we calculate what is the radius, and then based upon the fillet radius you again calculate all these stress concentration effects, again calculate the fatigue factor of safety. With the key seat, this is less than 1.5. We have a problem. So how do we fix this problem? Either we have to change the dimension or we have to change the material. We have to do something. Since we have made the calculations with a particular size, to redo all the calculations before will be a little bit tougher. So let's try by changing the material. Instead of 1020 steel, try 1050 cold drawn steel with SUT value slightly higher. Okay, so if you do that, again we have to calculate all the Merin factors, SE value, and for the given values we already have the KF and KFS values. We can utilize that. Let's see here, 1.74 according to the table over given over here. Let's see here. Okay, the SE value has changed. Q value is 0.72. Now why is this? Okay, I think they are recalculating KF and other values. Okay, so for the key seat, Again, they are evaluating Q and KF values. There is slight difference, and then evaluating, let's see here. Let's read through this. The key seat turns out to be more critical than the shoulder. We can either increase the diameter or use a higher strength material. Unless the deflection analysis shows a need for larger diameters, let us choose to increase the strength. So they have changed the material here. The Q and KF values ideally should not change. I don't know why they have changed here for the key seat. Let's see here. These values ideally should not change. We can use the same value here and then recalculate what is the fatigue factor of safety. Not sure why they changed over here. Let's see here. KF should not. Okay. Why the KF value changed? Because now it is clear. We have the SUT value which is different. 100 kpsi. So if you go to the Peterson's graph, based upon the SUT value, your KT value will change. Also the Q value will change. In the same way, KTS value and QS also will change. So we have to re-evaluate for each material as well. Whenever you change the material, SUT value changes. Here it is below it is 100 kpsi. In the previous case, we had a different material with a different SUT value. So therefore, these values also change. Recalculate them and calculate the fatigue factor of safety. And when we change the material, we get a better fatigue factor of safety, which is greater than 1.5. So this is right. We can proceed. Now remember that we also have a groove right at that point. Go back. There is a retaining groove. Okay, not clear here. So we can see there is a retaining groove over here. So this also will lead to very high stress concentration effects. And we have to take that into account. So let's see how they do the calculations with the retaining groove. Check at the groove at K, since KT has a flattened bottom. Grooves are often very high. For the torque diagram, note that no torque is present at the groove. Okay, so now we need to understand here we have included, for calculating the fatigue factor of safety, both the normal stress and the shear stress into account. But for the groove, we need only the bending moment. Why? Go back here. Where is the groove? Groove is located here. Now up till the key seat, we have the torque. Where is the torque diagram? Let's go below here. Up till this point J here, which is point J, up till the key seat here, we have the torque, and therefore we had to include the torque. But right after this point J, there is no more torque. Torque is 0. The only load which will act here is the bending moment load. Okay, so taking bending moment load into consideration, we calculate the amplitude of stress, which is completely reverse loading. And then for the given material, we can calculate what is the fatigue factor of safety with very high stress concentration effects, 5. Kf is equal to 5. Kf equal to Kt equal to 5 for bending moment load. Where did we get 5 from? Again, go back to the table. So when you design with the retaining ring groove, you have to consider for bending moment load 5. And that is the fatigue stress concentration factor that is used. And then we can calculate what is the fatigue factor of safety. We are in trouble again. What is the value? Is less than 1.5. We need to do some changes. So this is very low. We will look up the data for specific retaining ring to obtain KF more accurately. So that is an approximate way. So what we are going to do is we are actually going to consider what is the dimension of the retaining ring groove. Let us assume that we can get it from this website. What are the dimensions of the retaining ring? And based upon that shaft diameter, for the shaft diameter here 1.625 inches, we get the dimensions here, A, T, etc. What are these? These are the retaining ring grooves dimensions. Okay, and corner radius with the retaining ring groove, if you have fillet radius value r is equal to 0.01, we can calculate KT, KF and other values, KT, Q and KF values. Again, we evaluate based upon that what is the fatigue factor of safety, and we see for the actual values of the retaining ring. We have a fatigue factor of safety 1.5 greater than 1.5, and so work design is fine. So as you can see here, the design process for actual shaft is quite long. In your exams, you will not be asked questions, but we are just going through the procedure here. Okay. So now up till this point, we have only determined two diameters, D4 and D5. There are other diameters we have to determine, D4, D5. You have to determine D6, D7, D3, D1, D2. So all these diameters are there. We have to do the calculations for each of this. Okay. So again, you can go through the procedure here and we can see other diameters are calculated. Quickly check if point M might be critical. Again, they are checking point M. Let's see. Since I am shifting between two points again and again, let's keep the diagram here. Let's see if I can open the same problem in the book, so it will be easier for us to refer to. Okay, so Control F, shafts. And let's go to the problem in particular. Okay, so this is the problem we want to deal with. Okay, so where is the point M? Here we can see from the diagram over here. Point M is right over here. So we have the retaining ring groove, and we want to check whether in the shoulder we have very high fatigue factor of safety or lower fatigue factor of safety. Again, we can see at point M the torques are 0, so we can neglect torque and we will consider only the bending moment load. And the mean stress of a mean bending moment load is also 0, only we have the amplitude of stress. We can calculate sigma A by using the standard formula for the shaft and then determine whether our fatigue factor of safety is good. So this is also good, 1.5, but before that we needed to know the diameter of the shaft. So how did they obtain the diameter D6 here? Again, let's see here. We given any diameter of the shaft. So let's go back here. We have 1.625 over here, and he has assumed D6 as 1 inch. Okay. So from table 7, he obtained what is the stress concentration factor, since we do not know the diameter. And Let's see here what he has done. He has assumed D is equal to 1 over here, corresponding to D6. One inch. And then he proceeds with the calculation for fillet radius. Based upon the fillet radius is 0.02. Let's see. No. This is not D6. He has not assumed D6. I think D7 is assumed to be the 1 inch value. Okay. The smaller diameter right in this shoulder, he has assumed 1 inch diameter. So the smaller diameter will be 1 inch. And then based upon the fillet radius and other values, he may estimate what is D6. So let us see here, based upon the smaller radius, we have the stress concentration effect, and this value should be greater than 1.5, and therefore, let's see here, D7, selecting D7 to be 1 inch is fine. D7 is taken to be 1 inch. Okay. Let's see. The previous case, if we go back, okay, so the capital D over typical for supporting a shoulder, a typical value is 1.2. He has assumed typically 1.2 capital D or small d ratio. Let's see here. Again, we see here the smaller ratio is 1 inch, D7. And D6 is given here. Yeah, 1.625. Okay. Okay, so based upon the smallest value, D7 is taken to be 1.5 inches, and then he has evaluated that. From table 7.1, he has assumed KT equal to 2.7. Okay. So this is the table. If we go back to the slide again, KT equal to 2.7. So for a shoulder fillet here, he has assumed 2.7 from here. And we can evaluate D6 based upon the ratio capital D over small d can be evaluated on typical ratio value of 1.2. And if we assume that based upon the calculation, we can get D5 to be 1.2 inches here. But however, sorry, D7, D6, it should be D6, D7 and D6, yes. So based upon this ratio, D6 over D7 should be 1.2 typical values, and then D6 over 1. So D6 could be 1.2 inches or some other value. So he has taken a value greater than 1.2 inches and assumed it is 1.4 inches. Okay. Now we can select for D6 either 1.2 or 1.4, because if D7 satisfies the fatigue factor of safety, whatever size you assume for D6, it will also automatically satisfy the factor of safety. Okay, so therefore no more calculations are done, and this is the final design. Okay, so this is a very long calculation for the different diameters of the shaft. There are additional considerations we must take into account, especially deflection, and also in addition to deflection consideration, we also need to take into account resonance. So these are two things we will look at on Thursday. Okay, so see you guys, and I will meet you again on Thursday. Do you have any doubt up till this point? If you don't,
No, doctor.
okay, good. So we will meet again on Thursday. See you guys.